Hello friends, I welcome you in lecture number 24 on vector calculus. In this lecture we will discuss this question on verification of Green's theorem. This question was asked in GTU summer 2020 exam for 7 marks. The question is verify Green's theorem for line integral 2xy dx minus y square dy, where C is the boundary of the region bounded by the ellipse 3x square plus 4y square equal to 12. Now here it is not specified that which form of Green's theorem we have to verify. So we can go for tangential form, and if you recall, tangential form of Green's theorem is line integral m dx plus n dy along curve C equal to double integral over region R of del n by del x minus del m by del y, where R is the region enclosed by this curve C. And because we are asked to verify Green's theorem, we have to compute line integral as well as this double integral. So first we compare this integral with m dx plus n dy, and we find that m is 2xy and n is negative of y square. So first we write down all these given things here. Capital M is 2xy and capital N is minus y square, and we will require these partial derivatives. Partial derivative of m with respect to y, del m by del y, therefore del m by del y is 2x constant, derivative of y is 1, and partial derivative of n with respect to x is 0 because there is no term containing x here. And first we have to decide what is our region of integration for double integral, and boundary of that region is curve C, and here it is given that curve C is the boundary of the region bounded by the ellipse 3x square plus 4y square equal to 12. So first we rewrite this ellipse in standard form. Ellipse has equation 3x square plus 4y square equal to 12, and if I divide both sides by 12, I will have x square by 4 plus y square divided by 3 equal to 1, and this I can rewrite as x square divided by 2 square plus y square divided by square of root 3 equal to 1. And you can see, if you compare with x square by a square plus y square by b square equal to 1, then value of a is 2 and value of b is root 3, which is 1.7 something. Therefore value of a is greater than b. So this helps us to sketch the ellipse in xy plane. So now we try to sketch ellipse in xy plane, and value of a is 2 and value of b is square root of 3. So we will keep in mind that we have to go up to distance 2 on x axis, and on y axis we have to go up to 1.7 something. Okay, this is approximately 1.71. so suppose we just try to sketch the ellipse roughly. Suppose this is given ellipse, and we must have equal portion in each quadrant. This is just a rough sketch to explain the region of integration bounded by ellipse. So this point is 2, 0, and this much distance is square root of 3. So this point is 0 comma square root of 3. This will be 0 negative square root of 3, and on negative x-axis we have minus to 0. This is x-axis, so we should specify all these things. X-axis, here we have y-axis, and region of integration R is the region bounded by ellipse. Therefore this region shaded by red lines is the region R, over which we will have to find out double integral. And equation for this, and we will consider boundary of this ellipse as the curve C, and we will consider this counterclockwise orientation. So first we try to find out line integral along the boundary of this region, that is curve C, and then we will go for double integral. Now for line integral we have to find out parametric representation for this ellipse. So for that we can write this equation in this form. Suppose we write in this form: x by 2 whole square, x square upon 2 square can be written as square of x by 2. Similarly this I can rewrite as square of y divided by root 3 equal to 1. So from this we may have idea that if we consider x by 2 equal to cos t, y by root 3 equal to sin t, where t is running from 0 to 2 pi, because we have to consider the whole ellipse, boundary of whole ellipse. Therefore we should start from this and we have to complete full circle, and once we complete the one circle we will have 2 pi. So we will take x by 2 equal to cos t and y by root 3 equal to sin t for parametric representation for line integral. So first we compute line integral. First we compute line integral along boundary of the region, which is boundary of ellipse, and integral is 2xy dx minus y square dy. 2xy dx minus y square dy, and ellipse given curve C is, it has Cartesian representation as x by 2 whole square plus y divided by root 3 whole square equal to 1. The points on the ellipse must satisfy this equation: x by 2 whole square plus y by root 3 whole square equal to 1. And from this we have the idea for parametric representation. We consider x by 2 equal to cos t and y divided by root 3 equal to sin t, and we will vary t from 0 to 2 pi, and therefore x equal to 2 cos t and y equal to root 3 times sin t, and we will require derivatives of x and y with respect to t. Dx by dt is minus 2 sin t, and dy by dt will be equal to root 3 derivative of sin t is cos t, and therefore dx can be replaced by minus 2 sin t dt, and similarly dy can be replaced by root 3 cos t dt. So in our line integral we will replace dx by minus 2 sin t dt, dy by root 3 cos t dt, and we will replace x by 2 cos t, y by root 3 sin t. So using all these things, this line integral will be converted into integral of function of only one variable, which is t, and limits of integration will be from 0 to 2 pi. So now we write down that converted integral. Our line integral is integral of 2xy dx minus y square dy. 2xy dx minus y square dy. This we are writing as integral from 0 to 2 pi. Limits of integration for variable t are from 0 to 2 pi. We put x equal to 2 cos t. So first we write x equal to 2 cos t, y is root 3 sin t. Here we replace x by 2 cos t, y by root 3 sin t, and dx is minus 2 sin t, minus 2 sin t dt, minus we have y square, and y is root 3 sin t, therefore y square will be 3 sin square t. So here we write 3 sin square t for y square, and dy is root 3 cos t dt. So here we write root 3 cos t dt, and we simplify all these things. This is integral from 0 to 2 pi, and if you observe, we have 2 into 2 4, 4 into 2 8 into root 3 and with negative sign. So I have minus 8 root 3, and I have sin t 2 times in the product, therefore I have sin square t, and this cos t, and this dt I will take common, and here I have minus 3 times root 3 and sin square t into cos t, sin square t into cos t, and then we have integral with respect to. Okay, fine. Now you can observe that if we take sin square t cos t common, and then root 3 can also be taken common. So if we take this quantity common, we will have minus 8 minus 3 times root 3 sin square t cos t. If we take root 3 sin square t cos t common, here we are left with minus 8, and here we are left with minus 3. So we will have minus 11 root 3 sin square t cos t. So this is easy to understand, and in the next step I am writing that thing, and I will take minus 11 root 3 constant term outside the integral, minus 11 root 3 times integral from 0 to 2 pi sin square t times cos t integral with respect to t. So minus 8 root 3 minus 3 root 3, that is minus 11 root 3 into integral of sin square t cos t, minus 11 root 3. Now here we have this type of situation. We know this formula: if we have nth power of fx, and if derivative of fx is in the product, then this is equal to fx to the power n plus 1 divided by n plus 1. Instead of x, our variable is t, and here we can see derivative of sin t is cos t. It is in the product, and n equal to 2. So using this formula, this is sin cube t divided by 3, and limits of t are from 0 to 2 pi, and finally we put the limits. If we take t equal to 2 pi, we will have sin 2 pi raised to 3, sin 2 pi is 0, minus t equal to 0, that is sin 0, and we find that line integral is 0 along the boundary of the ellipse. Therefore line integral 2xy dx minus y square dy equal to 0, and we give this number 1. So this finishes first part of the question. We have answered half of the question. Because we have to verify Green's theorem, we have to compute line integral as well as double integral, and we have obtained value of line integral as 0. Now we will find out value of double integral, and we must have value of double integral to be 0. Otherwise we have made some mistake. Whatever answer we get for either of these two sides, we must have the same answer for other side. So here left hand side is line integral, its value is 0, therefore answer of double integral must be 0. Now for double integral we will have to decide the limits of integration. For that we rewrite our curve, which is ellipse, in another form. So from this I can write from this step y square by 3 can be written as 1 minus x square by 4, and this I can again rewrite as this is equal to y square, and here I take 4 LCM, so I will have 4 minus x square divided by 4 into 3, or 3 by 4 times 4 minus x square, and from this if I take square root on both sides, I will have plus or minus square root 3 divided by 2 square root of 4 minus x square. So we have rewritten equation of ellipse in another form, and from this we find that y has two values, root 3 by 2 square root of 4 minus x square and negative of this value. And suppose we decide to integrate with respect to y first and then with respect to x, then we will sketch a vertical line passing through the region to decide the limits of integration. So suppose I sketch this vertical line in this part. We can sketch vertical line in any part of the region. Suppose I consider this vertical line passing through the region of integration. Then this vertical line enters the region at this point and leaves the region at this point. This point is below x-axis and it is on the ellipse. So here we will write that negative value, minus root 3 by 2 square root of 4 minus x square. At this point y is negative. So here we mention that line enters in the region at the point where value of y is square root 3 by 2 into square root of 4 minus x square. So that we are writing from this step. We simplify the equation of ellipse and we obtain these two values of y, square root 3 divided by 2 square root of 4 minus x square and negative. And this point is also on the ellipse, and here line is leaving the region, and at this point we have y equal to positive square root 3 divided by 2 square root of 4 minus x square. So these two will be the limits of integration for variable y. Now to decide the limits of integration for x, we concentrate on the leftmost point of the region and rightmost point of the region. At the leftmost point, value of x is minus 2. So lower limit for integration with respect to x is minus 2, and on the rightmost point is having x equal to 2. So upper limit for x will be 2. Limits of variable x are minus 2 to 2, because for leftmost point value of x is minus 2 and at rightmost point value of x is 2. So we will consider these limits of integration for double integral, and now we compute double integral. So now we compute double integral over region R of the function del n by del x minus del m by del y, and here we choose integral first with respect to y and then with respect to x, and we have not written values of these partial derivatives. Okay, we have written del n by del x is 0, del m by del y is 2x. So here we write del n by del x equal to 0 and del m by del y is minus 2x. Integral is with respect to y first and then with respect to x, and this is nothing but we can take negative sign outside. Integral of 2x with respect to y first, and we have obtained the limits of y minus square root 3 divided by 2 square root of 4 minus x square, lower limit, upper limit is root 3 by 2 square root of 4 minus x square, and limits of x are from minus 2 to 2, and first we integrate with respect to y considering x as constant. So here outside I write integral with respect to x. Now here integral is with respect to y, so x is constant, and therefore this is going to be x is from negative sign is there, x is from minus 2 to 2, 2x as it is. Integral of 1 with respect to y is y, and limits are y equal to minus root 3 by 2 square root of 4 minus x square to root 3 by 2 square root of 4 minus x square, integral with respect to x. So be careful, here 2x as it is, integral of dy is y, and then we have written the limits for variable y. Now we put the limits of variable y and we simplify. So x is from minus 2 to 2, 2x as it is, upper limit is root 3 by 2 square root of 4 minus x square, minus lower limit is minus root 3 by 2 square root of 4 minus x square. So this is going to be 2 times root 3 by 2 square root of 4 minus x square, and then integral with respect to x. Because of negative sign of lower limit and this negative sign, we will have 2 times root 3 by 2 square root of 4 minus x square, and here 1 2 will cancel out, and we have 2 and 2 root 3 constant that we can take outside integral, and we are left with integral of x times square root of 4 minus x square with respect to x, from x equal to minus 2 to 2. And if you observe, we have this type of integral here, integral from minus a to a fx dx, and we know that if we have this type of limits which are negative of each other, and if our function is odd, then value of integral is 0. So here we can observe that x is odd function, this is even function, and product of odd and even function is always an odd function. So this is an odd function, and limits of integration are from minus 2 to 2. Therefore, using this result, we find that double integral is 0 over region R. Therefore, we write that double integral over R of del n by del x minus del m by del y is also having the same value as line integral has. So we give this number 1, number 2. Number 1 was given for the value of line integral, and therefore we have obtained the same answer for line as well as double integral, and therefore we can write that from 1 and 2 line integral along curve C m dx plus n dy, this is equal to double integral over region R double integral of del n by del x minus del m by del y. So this means we have verified Green's theorem. So therefore we can write that this says that Green's theorem is verified because we obtain this same value 0 for line as well as double integral. So here more work is required. Whenever we have problem related to verification, we have to compute line as well as double integral. So here first we compute line integral, and for that we are using this boundary of the ellipse. We write down the parametric equations for the boundary of ellipse, and using that parametric representation we find that line integral is 0. After that we compute this double integral, and for that we are choosing the order of integration as first with respect to y and then with respect to x. For that we consider a vertical line passing through the region, and we find out the value of y at which line is entering in the region and line is leaving the region. So these values of y will be the limits of integration for variable y, and for limits of integration for x we find out the value of x at leftmost and rightmost points, and then we find out value of double integral with these limits, and we obtain same value 0 which we had obtained for line integral. So in this way we can answer this type of questions on verification of Green's theorem. So this is all about this lecture. I hope you like it. Thanks for